if I told you that humanity's greatest journey has already reached its finale? That the moon landing wasn't our first step toward the stars, but rather our final glimpse outside a prison cell we might never actually escape. We grew up on stories of conquering Mars, colonies on Jupiter's moons, and interstellar arcs rushing to distant exoplanets. But what if all this is just a beautiful fantasy that crashes against invisible but absolutely unbreakable walls? Why haven't we moved a single centimeter past the modest lunar boundary in over 50 years? Is it just about money and political will, as we're often told? Or are there fundamental barriers, physical, biological, and maybe even existential, that turn our solar system into an impenetrable fortress and Earth into its only habitable tower? Today, we're going to look truth in the eye. We won't be discussing budgets or short-term missions. We're going to talk about the harsh laws of the universe, which are exactly the same for everyone, for us, and for any other hypothetical civilization. We are going to talk about the walls of our cosmic prison. And the main question we'll try to answer is this: is this a temporary confinement we'll eventually find a way out of, or a final life sentence? To understand why we are locked on our home planet, we need to start with the absolute basics. We have to figure out how movement actually works in the first place. In everyday life, we treat moving through space as something completely natural. When you walk down the street, your feet push off the asphalt. Friction is created. When a bird flies through the air, its wings push against dense atmospheric currents. When a ship sails, its propellers push away massive amounts of water. In all these cases, Isaac Newton's third law is at work. For every action, there is an equal and opposite reaction. To move forward, you have to push something backward. Here on Earth, we always have something massive and dense right at hand. The solid ground beneath our feet, the ocean, or a thick layer of air. But space is an absolute void, a vacuum. There's no asphalt, no water, no air. There's literally nothing to push off of. And this is where a colossal conceptual problem arises. If there is nothing around you, how do you force an object to fly forward? The only way to move in a vacuum is to bring mass with you and violently throw it in the opposite direction. This exact idea was finalized in the late 19th century by a schoolteacher from Kaluga, Konstantin Eduardovich Tsiolkovsky. This brilliant researcher ran the numbers while dreaming of interstellar flights. He derived a mathematical relationship that forever changed our understanding of space. In the scientific world, this relationship is known as the Tsiolkovsky rocket equation. Engineers sometimes call it something a bit darker: the tyranny of the rocket equation. Let's break this equation down. It goes like this. The final speed of a rocket equals the exhaust velocity of the gases leaving the nozzle, multiplied by the natural logarithm of the ratio of the rocket's initial mass to its final mass. That probably sounds like a dry academic abstraction. But let's translate those words into plain English. The equation is telling us this: for your ship to accelerate, you need to burn and expel fuel. But fuel has mass. And that means your engines have to push forward not just the ship itself, not just the astronauts and the payload, but also all that unburned fuel sitting in the tanks. Therefore, to lift the fuel, you need extra fuel. And to lift that extra fuel, you need even more fuel. It creates a vicious, endlessly expanding cycle. It's a mathematical progression that works against us. Just picture this analogy. Let's say you're going on a long road trip. You know there won't be a single gas station along the entire route. Your car burns a certain amount of gas per 100 miles. To make the whole trip, you have to bring your fuel supply with you. You load the trunk up with jerry cans. But now your car is significantly heavier. Because of this added weight, the engine starts burning more gas. You realize the gas in the trunk won't be enough. So you hook up a trailer to the back and fill it with barrels of gas. The mass of the car and the trailer gets so ridiculously huge that your tiny engine simply can't move the setup. You have to swap it out for a semi-truck engine, which guzzles fuel at an insane rate. And because of that, you're forced to hitch a second trailer full of fuel. That is exactly how rocket science works. Because of this paradox, spacecraft turn into gigantic fuel tanks, with a tiny capsule for humans or instruments tacked onto the very top. Let's look at a historical example. The famous American Saturn V rocket, which carried humans to the moon, weighed almost 3,000 tons on the launch pad. Just wrap your head around that number. 3 million kilograms of metal and highly explosive chemicals. But how much of that mass was actual payload delivered to lunar orbit? A laughably small amount. Only about 4% of the original weight. The other 96% was just fuel and massive metal tanks that were simply thrown away as they emptied out. 96%. Imagine a commercial cargo plane where, out of 100 tons of weight, 96 tons is just jet fuel, leaving only 4 tons for the actual plane, the pilots, the passengers, and the luggage. In Earth's economy, a transport system like that would bankrupt any company in a single day. But in aerospace, it's considered a triumph of engineering. It's the absolute limit of what our technology can do in the fight against gravity. You might ask, why don't we just invent more powerful fuel? Why use old technology when we could create superfuel? But here's the catch. We can't cheat chemistry. The energy of a chemical rocket engine comes from breaking and forming electron bonds between atoms. When we mix liquid oxygen and liquid hydrogen, the atoms rearrange themselves, forming water molecules and releasing a colossal amount of heat. The expanding hot gas blasts out of the nozzle and pushes the rocket up. The problem is that the periodic table is finite. We've studied all the available elements a long time ago, and we know exactly how much energy is hiding in those chemical bonds. The reaction of hydrogen with oxygen, or kerosene with oxygen, is basically the absolute ceiling for chemical efficiency. There is simply no magic substance in nature that would release 10 times more energy when burned and still remain stable. Any substance with a higher energy density stops being fuel and becomes an unstable explosive that would rip the engine to shreds right on the launch pad. We have hit the fundamental limit of chemical reactions. Our most powerful tool for overcoming Earth's gravity is operating at the absolute maximum of its theoretical potential. But why do we need so much energy in the first place? It's all because of our planet's gravity well. Earth is a massive sphere. It warps the space around it, creating an invisible but incredibly powerful pit. To break out of this pit and never fall back down, an object has to reach what's called escape velocity. On the surface of our planet, that speed is 11.2 kilometers per second. It's hard to intuitively grasp that number. 11.2 kilometers every single second. That is a speed 10 times faster than a bullet from a sniper rifle. And you have to impart that speed to a structure the size of a 30-story building, all while fighting the dense resistance of the atmosphere, which is trying to tear the hull apart through sheer friction. Some might argue, but what about alternative engines? Ion thrusters, plasma drives. Don't they solve the problem? It's true. engineers have developed ion engines. They work on a completely different principle. Instead of burning chemicals, they use an electric field to accelerate an ionized gas, like xenon, to incredible speeds. An ion engine shoots out particles dozens of times faster than the exhaust gases of a chemical rocket. That means it uses its mass way more efficiently. But here lies another paradox. Even though the exhaust velocity is massive, the actual mass of that material is minuscule. Because of this, the thrust of an ion engine is ridiculously low. A typical ion thruster pushes a spacecraft with about the same amount of force as a single sheet of paper pressing down on the palm of your hand. In a deep vacuum, where there's no resistance, this engine can fire for months, gradually pushing the ship to massive speeds. But it is completely useless on the surface of a planet. If you strap an ion engine to a rocket sitting on a launch pad, it won't move a single millimeter. Gravity instantly overpowers that faint thrust. As a result, we're forced to use gas-guzzling chemical engines just to break free from the planet's gravitational embrace. But what about nuclear thermal rockets? In the 1960s, researchers were actively developing the NERVA project. The idea was to run liquid hydrogen straight through the active core of a nuclear reactor. The hydrogen would instantly superheat and blast out, creating massive thrust. The efficiency of an engine like that is roughly twice as high as the best chemical counterpart. However, we run into insurmountable barriers once again. A nuclear reactor is a massive structure made of heavy metals and graphite. On top of that, it spews out lethal radiation. To protect the crew from the radiation of their own engine, you have to install a massive lead shield. That shield adds dozens of tons of dead weight to the ship. And right here, the rocket equation strikes back. To accelerate this heavy radiation shield, you need more hydrogen. And to hold more hydrogen, you need bigger, heavier tanks. Ultimately, the gain in engine efficiency is completely eaten up by the monstrous weight of the structure itself and its shielding. This is exactly why the rocket equation is called a tyranny. It's a ruthless mathematical law that accepts no compromises. It tells us the harsh truth. Lifting any payload off the surface of our planet will always require a gigantic expenditure of resources. Now let's apply this math to the idea of interstellar colonization. To establish a colony around another star, it's not enough to just send a flag and a few people in a cramped capsule. We would have to send self-sustaining infrastructure. Drilling rigs, reactors, construction equipment, medical centers, seeds, animals, and thousands of colonists. The mass of a hypothetical fleet like that would be measured in the millions of tons. If we barely managed to put a few tons of payload into orbit by burning thousands of tons of fuel, how much fuel would it take to launch a colonial fleet? Calculations show that the mass of the required chemical fuel would exceed the mass of all of Earth's oceans. It's a physical absurdity. The tyranny of the rocket equation is the first wall of our prison. It proves that Earth's gravity has us in an iron grip. You can send a few people into low Earth orbit to run science experiments. You can launch an automated probe to the edge of the solar system, spending decades and billions of dollars to do it. But you cannot mass transport infrastructure and civilization across the void. We've learned to do a little jump over the edge of our gravity well to peek around. But we are still stuck at the bottom. And the math shows that we will never have enough energy to pull our entire species out of it. But the sheer difficulty of getting payloads into orbit is just the most obvious problem. It's only the beginning of our list. Let's assume for a second that we pulled off a miracle. Let's say we somehow bypassed the rocket equation and built a colossal ship right in outer space, assembling it out of asteroids. Could we then set off for the stars? Unfortunately, no. As soon as we solve the mass problem, a second, even more insurmountable barrier will rise up to block our path. A barrier we rarely think about when we look up at the night sky. In the next chapter, we're going to dive into how our brains are completely unequipped to truly grasp the scale of the void, and why cosmic distances render any journey pointless. To grasp our main problem, we have to talk about how the human brain works. Over the course of long evolution on the surface of the Earth, our minds perfectly adapted to solving very specific tasks. Our ancestors learned to estimate the distance to the nearest water source, calculate the trajectory of a thrown spear, or figure out how many days of travel separated them from a neighboring tribe. We intuitively understand what meters and kilometers are. It's easy for us to picture the commute from home to work. We can imagine a trip to another continent taking a few hours on a plane. But our biological hardware is completely unequipped to process cosmic scales. When astrophysicists rattle off numbers describing the distances between stars, our brains simply refuse to process them. They turn these colossal figures into abstract noise. We hear the words, but we don't feel their true weight at all. Let's try to break this psychological barrier and feel the true scale of the emptiness we're floating in. In outer space, distances are so incredibly vast that measuring them in kilometers is totally pointless. Scientists use a different unit, the light year. That is the distance a beam of light travels in 1 Earth year. Light is the fastest phenomenon in the universe. In an absolute vacuum, it cruises at a speed of 300,000 kilometers per second. Just think about that number. 300,000 kilometers in a single second. If a beam of light could travel in a circle, it would wrap around the Earth's equator 7.5 times in the time it takes you to say the word 1. Light travels from the Earth to the Moon in just 1.3 seconds. That's our closest cosmic neighbor. It takes light 8 minutes and 20 seconds to travel from our Sun to Earth. That means whenever you look at the Sun during the day, you are always seeing it as it was over 8 minutes ago. Now let's look at the closest star system to us. It's called Alpha Centauri. It's actually a 3-star system, and the closest one is called Proxima Centauri. The distance to it is 4.24 light years. In sci-fi movies, spaceships cross distances like this in a couple of hours of screen time by pulling off a flashy hyperspace jump. The stars out the window blur into glowing lines, and the audience gets a rush of adrenaline. But in the real universe, things work differently. 4.24 years of travel at the speed of light. If we convert that into the kilometers we're used to, we get a number close to 40 trillion kilometers. 40 trillion. That's a number with 13 zeros. Our brains can't visualize that. So let's use a thought experiment and build a scale model. Imagine we shrank our giant blazing sun down to the size of a standard soccer ball. We place this ball right in the middle of a large empty field. Where would Earth be in this model? Our home planet would turn into a tiny grain of sand, about 2 millimeters across. And this grain of sand would be orbiting the soccer ball at a distance of roughly 25 meters. You could walk that distance in a few seconds. Where would Jupiter be? The biggest planet in our system. It would be a small glass marble sitting about 130 meters away from the ball. And where would the orbit of Pluto be? The dwarf planet on the outskirts of our system. Pluto would be a speck of dust about 1 kilometer away. We're already dealing with a huge area. A soccer ball, and a full kilometer away from it, a few scattered specks of dust are flying around. All the rest of the space between them is a ringing, freezing, absolute void. But the real kicker starts now. In our shrunken down model, where the sun is a soccer ball, where is Alpha Centauri? We need to take a second soccer ball and place it where the neighboring star is located. How far do you think we'd have to walk? 10 kilometers? 100? No. In this scale model, the second soccer ball would be located roughly 7,000 kilometers away from the first one. That's like placing one ball in Moscow and the other somewhere in the Far East or in Central Africa. And across all that colossal space between the two balls, there is absolutely nothing. Not a single tiny planet, not a single large asteroid. Just a vacuum, a few stray hydrogen atoms, and a crushing, overwhelming loneliness. This is exactly the space that interstellar colonization enthusiasts want us to cross. Let's look at our current technological capabilities. In 1977, humanity launched the automated interplanetary probe, Voyager 1. It is a masterpiece of engineering. It used gravity assists around the gas giants to slingshot itself to unbelievable speeds. Right now, Voyager 1 is flying away from the sun at about 17 kilometers per second. That's faster than a speeding bullet, faster than anything you've ever seen on Earth. Recently, this tiny spacecraft crossed the boundary of the heliosphere and entered interstellar space. But if we aimed Voyager 1 directly at the Alpha Centauri system, how long would it take to cross those 40 trillion kilometers? The answer crushes any dreams of quick colonization. At a speed of 17 kilometers per second, it would take the Voyager 1 probe about 73,000 years just to reach the nearest star. 73,000 years. Let that sink in. All of recorded human history spans maybe 5,000 years. Tops. The ancient Egyptian pyramids were built about 4,500 years ago, and we're talking about a journey that would last over 70 millennia. By the time the ship reaches its destination, Earth could go through geological epochs, entire continents could vanish, and humanity itself could evolve into something totally different, or disappear without a trace. You might say, but Voyager 1 is old technology from the last century. Surely we'll be able to fly faster in the future. All right, let's assume we make an unbelievable technological leap. Let's say we somehow solve the tyranny of the rocket equation from Chapter 1 and build a super powerful nuclear engine that can accelerate a massive colony ship to 1% of the speed of light. That is a colossal speed. 3,000 kilometers every single second. Even at that mind-bending speed, the flight to Alpha Centauri would take over 400 years. 4 centuries stuck in a metal tube, surrounded by a lethal vacuum. And here, we run into another brutal reality of the void. Outer space isn't actually completely empty. Yes, there's no air, but there is interstellar dust and microscopic bits of rock. Under normal conditions, they aren't a threat. But when your ship is ripping through space at thousands of kilometers a second, the laws of kinetic energy turn these invisible specks of dust into weapons of mass destruction. An object's kinetic energy depends on its mass and the square of its velocity. If you are flying at 1% of the speed of light, hitting a tiny grain of sand weighing just 1 gram would release energy comparable to detonating dozens of kilograms of TNT. Your ship would simply be ripped to shreds before the crew even realized what happened. To protect yourself against collisions like that, you'd have to mount an unbelievably thick armored shield on the front of the ship. But we already know from the previous chapter that adding mass to the ship makes it nearly impossible to accelerate because of the lack of fuel. We end up in a fatal logic trap. You want to fly fast so the trip doesn't take hundreds of centuries. But the faster you fly, the thicker the armor you need. The thicker the armor, the heavier the ship. The heavier the ship, the slower you fly. On top of that, the true scale of the void puts strict limits on communication and control. Imagine your ship actually sets off. A few decades pass, and it's halfway to its destination. Suddenly, there's a serious accident on board. The life support system fails. The crew sends a distress signal back to Earth, asking for help or advice. A radio signal travels at the speed of light. If the ship is 2 light years away from us, the signal will take exactly 2 years to reach engineers on Earth. The engineers on Earth will get the message, spend a month analyzing the problem, and send back a repair manual. That manual will take another 2 years to fly back to the ship. So, from the moment the distress call is sent to the moment an answer is received, over 4 years will pass. By that time, the crew will have long since suffocated or frozen to death. In deep space, you are completely alone. Tech support is physically impossible. Your isolation is absolute. This brings us to the psychological aspect of the problem. Evolution made us social creatures, tied to a dynamically changing environment. We need the changing of the seasons, the sounds of nature, the feeling of solid ground under our feet. Putting a human in the confined space of a metal capsule flying through eternal darkness is an unimaginable test for the psyche. The stars outside the window won't be zooming by. Because of the colossal distances, the view outside won't change for decades. You'll be staring into a dark abyss where glowing dots look like they're nailed to a black canvas. It is sensory deprivation on a planetary scale. The human mind, faced with the true face of infinity and realizing its own insignificance against these distances, risks spiraling into the deepest depression. In this way, the vacuum of space acts as the perfect insulator. It's not just a distance you have to cross. It is a quarantine zone set up by nature itself. The universe is designed to keep matter and biological life locked down in local safe havens around warm stars. Sometimes we think that if the only problem is speed, then surely scientists in the distant future will find a way to bypass this limit. We hold out hope for the discovery of wormholes or warp drives that bend space. We want to believe that physics hasn't spoken its final word. But this hope shatters against the most fundamental and unbreakable law of the universe. It turns out the universe has set a strict speed limit, and trying to get close to that limit triggers mechanisms that literally break the very fabric of time and mass. In the next chapter, we're going to break down the energy barrier and the special theory of relativity. We'll find out why Einstein's physics makes the idea of fast interstellar travel not just technically difficult, but mathematically absurd. In the previous chapter, we grasped the overwhelming, chilling scale of the cosmic void. We found out that even the star closest to us is sitting at a distance of almost 40 trillion kilometers. When the human mind comes up against such a massive, insurmountable distance, it instinctively looks for the simplest and most logical solution. If the distance is so vast, that means we just need to move faster. Doesn't that make sense? When we need to quickly cross an ocean, we don't sail on a wooden raft. We get on a jet plane. Therefore, to cross the galaxy, we just need to invent an incredibly fast engine, step on the gas, and blast through the void. However, this is exactly where the strictest and most unforgiving force in our universe steps in: the special theory of relativity. In 1905, a young clerk at the Swiss Patent Office named Albert Einstein published a paper that forever changed our understanding of space and time. Einstein proved that the speed of light isn't just the speed at which photons travel through a vacuum. It is the fundamental speed limit for the transfer of any information and any interaction in our world. This limit is exactly 299,792,458 meters per second. For convenience, we often round this number to 300,000 kilometers per second. Light moves incredibly fast, but the main point is that nothing in the material world is capable of moving faster. This is an absolute law of physics. But why can't we break this rule? Why can't we build a rocket that accelerates to 301,000 kilometers per second? To understand this, we have to look at the most famous equation in the history of science. That equation states energy equals mass times the speed of light squared. We usually treat mass and energy as totally different things. Mass is something solid, material. A rock has mass. And energy is something ephemeral, like heat from a fire or the movement of the wind. But Einstein showed that mass and energy are two sides of the same coin. They can transition into each other. Mass is incredibly tightly packed energy, and energy has a mass equivalent. Now let's apply this law to our interstellar ship. When you fire up the engines and start accelerating, you are giving the ship kinetic energy. The ship starts moving faster and faster. But because energy is equivalent to mass, adding a colossal amount of kinetic energy makes your ship heavier and heavier in terms of inertia. At the low speeds we're used to on Earth, this effect is so tiny it's impossible to notice. When you accelerate your car on the highway, its mass technically increases by microscopic fractions of a gram. But when you try to accelerate a giant starship to a speed that makes up a significant chunk of the speed of light, the situation spirals out of control. Imagine this thought experiment. You're pushing a shopping cart in a supermarket. At first, it's empty, and you easily get it up to a light jog. But imagine that with every mile per hour you add to its speed, heavy bricks magically drop into the cart. The faster you run, the heavier the cart gets, and the more physical effort you have to exert just to keep accelerating. At some point, the cart will weigh as much as a freight train, and you simply won't be able to move it a single millimeter further, no matter how much energy you spend. This is exactly what happens to any material object approaching the light barrier. If you want to accelerate a ship to 90% of the speed of light, its inertial resistance will multiply massively. To add just 1 more percent, you'd need to put in more energy than you spent on all the previous acceleration. And to reach 100% of the speed of light, you would need an infinite amount of energy. Infinite. Not just all the energy of our sun or the entire galaxy, but a mathematical infinity, which simply does not exist in our physical world. But let's come back down to Earth and look at what seem to be more modest numbers. Let's assume we aren't trying to reach the speed of light. We just want to accelerate our ship to at least 10% of that limit. That's 30,000 kilometers per second. At that speed, a flight to the nearest star will take a little over 40 years. That's a time frame comparable to a human lifespan. Sounds optimistic. Let's take a ship with a mass of 420 tons as an example. That's the mass of the International Space Station. A pretty modest size for an interstellar arc that has to keep a crew alive for decades. To accelerate a mass of 420 tons to 10% of the speed of light, it would require a colossal amount of kinetic energy. To put that into familiar terms, we would need energy far exceeding the entire global consumption of electricity, oil, gas, and coal for a whole year. And that is just to accelerate this tiny ship. At the end of the journey, so you don't overshoot the target planet, you will need to brake. which means you will need the exact same colossal amount of energy to slow down. Therefore, you have to carry a supply of fuel with you just for stopping, which brings us right back to the tyranny of the rocket equation from Chapter 1. The mass of the fuel increases the mass of the ship, which requires even more energy to accelerate it in the first place. This is where many space enthusiasts pull out their ultimate trump card. They say, forget about chemical rockets. Forget even about nuclear reactors. The future belongs to antimatter. The concept of antimatter was predicted by the brilliant physicist Paul Dirac in 1928. Dirac's equations showed that for every particle in our universe, there should be a twin particle with the opposite charge. The electron has the positron, the proton has the antiproton. The most amazing feature of antimatter is the process of annihilation. If you combine 1 gram of regular matter with 1 gram of antimatter, they completely destroy each other, turning into pure energy. The efficiency of this process is 100%. For comparison, the nuclear fission happening in modern atomic reactors converts only about 0.1% of uranium's mass into energy. It seems like this is it, the perfect fuel for stellar travel. An antimatter engine could accelerate a ship to unbelievable speeds using a minimal amount of propellant. However, nature doesn't hand out freebies. The problem with antimatter is that it's not just sitting out there in nature for us to take. We can't mine it from asteroids. To get antimatter, we have to create it ourselves. Right now, we know how to do that in giant particle accelerators, like the Large Hadron Collider. We smash particles together at massive speeds and collect antimatter bit by bit, literally atom by atom. This process is unbelievably energy intensive and monstrously inefficient. Creating 1/1000th of a gram of antimatter burns up a massive amount of Earth's electricity. According to current estimates, to produce just 1 gram of antihydrogen using existing tech, humanity would have to run the collider non-stop for millions of years, and the cost of that single gram would be in the tens of trillions of dollars. But let's say we found a magical way to produce antimatter by the ton. The next unsolvable problem arises: how do we store it? Antimatter reacts with everything. Any contact with the wall of the tank will instantly trigger a catastrophic explosion. To hold it, scientists use what are called penning traps, highly complex devices that create strong electromagnetic fields where the particles hover in a vacuum, touching absolutely nothing. These traps consume constant energy. They require massive cooling systems and heavy magnets. To safely store 1 kilogram of antimatter, you would need an installation weighing thousands of tons. And once again, the math of the flight crumbles to dust. The perfect, lightweight fuel requires such heavy infrastructure just to store it that the entire gain in energy density drops to 0. But let's go even further. Let's pretend we've solved absolutely every technological problem. We have lightweight antimatter, we have invisible tanks, and we are flying toward the stars at speeds of tens of thousands of kilometers per second. It is exactly at these relativistic speeds that the vacuum of space stops being just empty. It turns into a deadly environment flooded with lethal radiation. In space, there is what's called the cosmic microwave background, CMB, a faint microwave echo left over from the Big Bang. Under normal conditions, it's completely harmless. But when your ship is ripping through space at sublight speeds, the Doppler effect kicks in. Everyone knows this effect. When a car with a siren comes rushing toward you, the pitch of the siren sounds higher. And when the car drives past and moves away, the pitch drops sharply. Electromagnetic radiation behaves the exact same way. When you fly through outer space at massive speeds, the faint microwaves of the CMB as well as the light from stars dead ahead of you, experience what's called a blue shift. For the ship, these harmless waves compress and turn into streams of hard X-ray and gamma radiation. Think of a simple analogy. Imagine you're walking in a light, barely drizzling rain. The drops fall softly on your face without causing any discomfort. But if you stick your head out the window of a sports car speeding through that same light rain at 120 miles per hour, those exact same drops will hit your face like gravel. At relativistic speeds, light and stray atoms of interstellar hydrogen hit the ship's hull with such incredible energy that they literally scorch the material. This effect is somewhat similar to Cherenkov radiation, where particles move through a medium faster than the phase velocity of light in that medium, creating an eerie blue glow. But in our case, this glow won't just be a pretty visual effect. It will be a blast of lethal radiation generated purely by the fact that you are moving fast. To protect the crew from this man-made radiation storm, the ship would have to be outfitted with an incredibly thick layer of armor plating. For example, a multi-meter layer of lead, or a giant tank of water at the front. And once again, we fall right into the same trap. The armor weighs thousands of tons, and to accelerate those tons, we need even more fuel, which we can't take on board. But even if we ignore the problems of fuel, radiation, and mass, the theory of relativity will deliver one final, most brutal blow. This blow isn't aimed at the metal of the ship, but at the very essence of human life. We are talking about relativistic time dilation. The faster an object moves through space, the slower time passes for it relative to those who stayed behind. This isn't an optical illusion or a trick of perception. It is a fundamental property of the fabric of the universe. Suppose a group of colonists sets off for a star 100 light-years away from Earth. They are flying on a ship traveling at 99% of the speed of light. According to the calculations of Lorentz transformations, time on board this ship will slow down by a factor of about 7.1. For the astronauts, this long journey will take about 14 years. They will age 14 years, celebrate 14 birthdays. They might survive this trip. But when they reach their destination and check their watches to send a triumphant message back home, they will realize a terrifying truth. Back on Earth while they were flying, a little over 100 years have passed. All the people who built their ship, all the engineers who saw them off at the launch pad, all their children and grandchildren are long dead. Earth's civilization has leaped an entire century into the future. The political system might have changed. The languages might have shifted. And what if the colonists want to come back? That's another 14 years of travel for them, and another 100 years will pass on Earth. By the time they return, their home planet will have aged 2 centuries, while they themselves will only be 28 years older. A flight like that isn't the expansion of the human empire. It is an act of voluntary exile. Interstellar travelers permanently cut themselves off from human history. You can't build a unified civilization tied together by trade, culture, or governance if a courier carrying a message travels into a future from which there is no return to a synchronized present. The time difference turns every colony into a totally isolated island. So, the universe's energy barrier doesn't just forbid us from flying fast due to a lack of resources. It makes the very concept of fast travel physically destructive and chronologically pointless. The laws of thermodynamics and Einstein's postulates are heavy deadbolts on the doors of our prison cell. But let's forget about engines, speeds, and time paradoxes for a moment. Let's assume we've accepted that the flight will be slow, and we are ready to fly for thousands of years using modest, available technology. It turns out that even then, the universe has set up a barrier for us, and this barrier is invisible to the human eye. but it can tear down any biological structure faster than running out of oxygen. In the next chapter, we're going to talk about radiation, not the kind we create by accelerating, but the kind that permeates every cubic meter of calm and seemingly silent deep space. We have already figured out that the laws of thermodynamics and the theory of relativity won't let us move fast. The massive weight of fuel and energy limits force us to accept the fact that any space journey is going to be long. Very long. If we want to head to another star, or even out to the distant edges of our own solar system, the flight will take years, decades, or even centuries. But it is exactly here, in this forced slow motion, that we run into a new, lethal threat. We often think of space as just the absence of everything, a void, a vacuum, a place where nothing happens. But in reality, the space between planets and stars is filled with an invisible, chaotic, and highly destructive storm. To understand the core of this threat, let's look at the place we are right now. Earth isn't just a ball of rock. It's an incredibly complex and powerful spaceship equipped with a multi-layered defense system. Right in the center of our planet is a core of molten iron and nickel. It's constantly spinning, and this movement creates a colossal dynamo effect. As a result, a magnetosphere forms around the Earth, a giant invisible shield that stretches tens of thousands of kilometers out into space. But that's not all. Beneath this magnetic shield is a second layer of defense, our dense atmosphere. If you converted the density of the air above our heads into the equivalent of water, it turns out we are constantly living at the bottom of an ocean 10 meters deep. This thick layer of air acts as a perfect shock absorber. We evolved over the course of 4 billion years in conditions of absolute safety. Our biological species has never had to face what is raging outside the atmosphere. And what's raging out there is radiation. But when physicists talk about cosmic radiation, they don't mean the kind of radiation we deal with in an X-ray room or at a nuclear power plant. Cosmic radiation has a different nature. These are streams of subatomic particles ripping through space at speeds close to the speed of light. The first source of this radiation is right next door. It's our sun. In the mid-20th century, the brilliant astrophysicist Eugene Parker predicted the existence of what we call the solar wind. He proved that a star doesn't just shine. It is constantly blasting out streams of protons and electrons in every direction. But the solar wind is just a light breeze compared to solar flares. From time to time, the magnetic fields on the surface of the sun twist and snap, releasing energy equivalent to detonating millions of nuclear bombs. In that moment, a colossal cloud of highly energetic particles is hurled into space. If a spaceship gets caught in the path of one of these blasts without proper shielding, the crew will receive a lethal dose of radiation in just a few hours. The onset of acute radiation sickness will be fatal before the astronauts even have time to contact Earth. But the scariest part is that solar flares are practically impossible to predict. We might spot a flare through a telescope, but by the time we see it, the stream of particles is already halfway to the ship. The crew will have mere minutes to take cover. But let's assume we build a small, heavily armored capsule inside the ship, a sort of panic room where the crew can wait out a solar storm. Does that solve the problem? Unfortunately, no. Because once we leave the solar system, something much more sinister is waiting for us. This phenomenon is known as galactic cosmic rays. It's a pretty heavy topic, but let's break it down. Galactic rays come to us from deep space. They are born from the most catastrophic events in the universe, during supernova explosions, or in the accretion disks around supermassive black holes. Unlike the protons of the solar wind, galactic rays are the heavy nuclei of atoms. Picture an iron atom where monstrous forces have ripped away absolutely all of its electrons, leaving only the bare, heavy nucleus. And then a supernova explosion accelerates this nucleus to almost the speed of light. A particle like that carries horrific kinetic energy. The analogy here writes itself. If a solar wind proton is a flying grain of sand, then a heavy galactic ray ion is a cannonball flying at the speed of a hypersonic missile, just on a microscopic scale. What happens when a particle like that hits a human body? Our bodies are made of cells, and inside every cell is a nucleus containing a DNA molecule. DNA is an incredibly complex instruction manual written by nature that controls all of our life processes. When a heavy ion punches through a cell, it leaves behind what's called an ionization track, a zone of absolute destruction. It severs chemical bonds, smashes water molecules into aggressive free radicals, and literally tears the double helix of DNA in several places all at once. Cells know how to repair minor damage, but when the helix is ripped to shreds by a heavy ion, the repair mechanism glitches out. The cell either dies, or much worse, starts dividing uncontrollably. That is exactly how cancer starts. This reminds me of a story from the Apollo program days. When the astronauts were flying to the moon, they started noticing a weird thing. Even when they were in a pitch-black cabin with their eyes closed, they would periodically see bright flashes of light. At first, they chalked it up to fatigue or stress. But later, scientists figured out the true nature of this phenomenon. Heavy galactic ray particles were shooting right through the hull of the ship, piercing the astronaut's skull, and passing straight through the vitreous body of their eye. Moving through the fluid of the eyeball, the particle generated a tiny flash of light, that same Cherenkov radiation. The astronauts were literally seeing the radiation that was destroying their nervous systems at that exact moment. And this brings us to how space affects the brain. Long-term exposure to galactic rays doesn't just spike the risk of cancer. Animal testing has shown that heavy ions methodically wipe out neural connections. Mice subjected to radiation mimicking cosmic levels showed a sharp drop in cognitive function, memory loss, and heightened anxiety. If you send a human on a flight for a few years, by the end of the trip, they might lose the ability to solve complex problems, forget their training, and sink into deep paranoia. So how do we shield ourselves from this threat? The most obvious answer is to add armor. If particles are punching through thin metal, it means we need to make the ship's walls thicker. But here a paradox kicks in that makes the situation hopeless. If you strap an aluminum plate a few centimeters thick to the ship, not only will you fail to protect the crew, you will actually make the radiation background inside the ship several times more lethal. Why? Because when a heavy galactic ray ion slams into an aluminum atom in the hull at massive speeds, a nuclear fission reaction happens. The ion shatters the metal atom to pieces. Instead of just one particle, a whole spray of secondary radiation blasts inside the ship, a cascade of neutrons, protons, and gamma rays. It's like firing a handgun into a glass wall. The bullet might miss you, but you'll be shredded by thousands of sharp shards. To stop both the primary rays and the secondary cascade of neutrons, you need special shielding. Materials rich in hydrogen work best, because light hydrogen atoms absorb neutrons well without spawning shrapnel. The perfect candidate is just normal water or dense plastics like polyethylene. But according to physicists' calculations, to create a radiation background inside the ship comparable to Earth's, you'd have to surround the living module with a layer of water about 3 meters thick. on all sides. Let's picture a living module the size of a small house, where colonists will spend years. If you surround it with a 3-meter layer of water, the mass of that water shield will be in the thousands of tons. And here we are, slamming full speed right back into the tyranny of the rocket equation from Chapter 1. How do you get thousands of tons of water into orbit? How do you then accelerate this insanely heavy water cocoon to a speed that lets you reach another planet in a reasonable amount of time? The answer is simple. You don't. We don't have enough fuel in the whole world. Engineers offer an alternative: active magnetic shielding. The idea is to create an artificial magnetic field around the ship, just like Earth's. We could use giant superconducting magnets to deflect charged particles away from the hull. It sounds like an elegant solution straight out of a sci-fi novel, but in practice, it creates new barriers. To generate a field strong enough to deflect heavy ions flying at relativistic speeds, you would need magnets of colossal size. Those magnets have to be cooled to temperatures near absolute zero, which requires massive refrigeration systems. On top of that, they consume an unbelievable amount of energy, which means you'd need a powerful nuclear reactor to power them. And the reactor, the cooling systems, and the magnets themselves all add hundreds of tons to the ship's mass again. The trap snaps shut. Any attempt to shield against radiation leads to a critical mass increase, making the flight impossible. We have hard data backing up the scale of this problem. In 2012, the Curiosity rover was sent to Mars. Inside, it was an instrument designed to measure radiation levels. The trip to Mars took a little over 8 months. The data showed that during a one-way flight, an astronaut would receive a radiation dose of about 300 millisieverts, and a full mission to Mars and back would deliver a dose of about 1 full sievert. For comparison, the maximum allowed dose for nuclear industry workers on Earth is just 50 millisieverts a year. A dose of 1 sievert increases the risk of fatal cancer by 5%. And that's just a short hop to the next planet over. If we are talking about a colonial voyage to the edge of the solar system that will take decades, the accumulated dose is guaranteed to kill the entire crew. It paints a fascinating and terrifying picture. Galactic radiation is the perfect, all-encompassing quarantine mechanism. It's as if the universe is telling us, you are only allowed to exist under the protective blanket of your home planet. The second you leave the safety of the magnetosphere, the very fabric of space begins slowly, but ruthlessly dismantling your complex biological molecules. We were built for this specific place. Our bodies are not capable of existing in the void. But the problem isn't just the external assault of radiation. It turns out that even if we lock ourselves away from radiation completely, our own bodies will start destroying themselves from the inside, due to the lack of a fundamental force we are used to. In the next chapter, we're going down to the physiological level to figure out why gravity keeps us on a leash, and how prolonged weightlessness turns the human body into something totally non-viable in deep space. We are used to thinking of ourselves as explorers and conquerors. It feels like the human mind is totally independent of its physical shell, and if we can invent a spaceship, our bodies will obediently follow our minds into any depth of the universe. But in reality, the situation is a lot more complicated. The problem is that we don't just live on Earth. We are its direct physical extension. Let's break this down a bit more. Over the course of nearly 4 billion years of continuous evolution, life on our planet developed under the strict dictate of one absolutely unchanging parameter. That parameter is gravity. The acceleration of free fall on Earth's surface is 9.8 meters per second squared. Or, As physicists often call it, 1G. Every cell in your body, every bone, every blood vessel, and every molecule of fluid inside you was engineered by nature with this specific pulling force in mind. Earth literally molded us to fit it. In the moment we rip the human body out of these familiar conditions and drop it into zero gravity, our body starts rapidly adapting to the new environment. But in the context of spaceflight, this adaptation equals slow systemic destruction. Let's start with the most obvious thing, our skeleton. On Earth, our bones are constantly under mechanical stress. They have to hold up the weight of our body against gravity. Bone tissue isn't just a dead calcium frame. It is a living, incredibly dynamic system. Two types of cells are constantly at work inside it: osteoclasts and osteoblasts. Osteoclasts are busy constantly breaking down old bone tissue, and osteoblasts immediately build new bone right in its place. This renewal process is regulated by mechanical pressure. When you walk, run, or just stand there, microscopic deformations in the bone send a signal to the osteoblasts. We need strength here, build new material. But what happens in the weightlessness of space? The mechanical stress completely disappears. Your skeleton serves no useful purpose anymore because your body weighs nothing. The signals stop. The osteoblasts, getting no orders to act, sharply slow down their work. But the wrecking crew, the osteoclasts, keep working away at their usual pace. As a result, the body literally begins to dissolve its own skeleton. Medical studies conducted on orbital stations show terrifying statistics. In zero gravity, an astronaut loses between 1% and 2% of their bone mass every month. If a flight to a neighboring star system, or even to the outer planets of our own system, takes several decades, the crew's bones will turn into a fragile, porous sponge. If they attempt to land on a planet with even minimal gravity, the colonists' skeletons will simply snap under the weight of their own bodies. The calcium that washes out of the bones dumps into the bloodstream and settles in the kidneys, forming massive kidney stones, which without access to surgery would lead to agonizing consequences. And that is just the beginning of the physiological collapse. The next problem is hiding in our cardiovascular system. On Earth, gravity is constantly pulling our blood and other fluids down toward our feet. To make sure the brain gets enough oxygen, our heart has to work like a high-powered pump, fighting Earth's gravity to push blood upward. The blood vessels in our legs have a complex system of valves and strong muscle tone to keep blood from pooling at the bottom. When an astronaut ends up in space, gravity vanishes, but the heart, out of habit, keeps pumping blood into the upper body with massive force. A massive fluid shift happens. About 2 liters of blood and lymph rush from the legs up into the chest and head. This is exactly why astronauts' faces often look puffy in photos from orbit, and their legs get unnaturally skinny. This excess fluid in the upper body puts colossal pressure on the optic nerve and the back of the eyeball. This leads to what's called spaceflight-associated neuroocular syndrome. The eyeball literally gets flattened from behind, and the shape of the cornea changes. About 70% of astronauts coming back from long missions complain of permanent vision loss. In the long-term context of an interstellar flight, this means the crew could just go blind before they even reach their destination. But the deepest changes happen on a genetic level. In 2015 and 2016, the U.S. Space Agency ran a unique biological experiment called the Twins Study. The focus was on 2 astronaut brothers with identical genes, Scott and Mark Kelly. Mark stayed on Earth as the control subject, while Scott went up to the space station for almost a full year. The results of this experiment published in the prestigious journal Science, gave biologists a lot to think about. It turned out that spending a long time in space triggers massive epigenetic shifts. In Scott, the activity of over 10,000 genes changed. His immune system was in a state of constant, unexplained stress, as if his body were constantly fighting off a severe, invisible infection. A weird thing happened with his telomeres, too. The protective caps on the ends of chromosomes that dictate cellular aging. In space, Scott's telomeres unexpectedly grew longer, which at first looked like a sign of reverse aging. But the second he returned to Earth and was exposed to normal gravity, those telomeres rapidly shrank, ending up even shorter than they were before the flight. Accelerated cellular aging had kicked in. His DNA was damaged, and his gut microbiome was altered beyond recognition. And this is where many engineers and space fans offer up a classic sci-fi solution. They say, if the problem is zero gravity, let's just make it artificially. Let's build a giant, rotating, ring-shaped ship. Centrifugal force will pin people against the outer edge of the ring, and they'll feel right at home. Sounds logical? But physics throws up an unbeatable barrier once again. There's something called the Coriolis effect. If you are inside a spinning drum with a small radius, the difference in rotational speed between your feet glued to the floor and your head will be too extreme. Every time you turn your head, the fluid in your inner ear will slosh in different directions. Your vestibular system will go haywire. It causes non-stop, violent nausea, loss of spatial awareness, and makes doing even the simplest task impossible. According to engineering calculations, for the Coriolis effect to be unnoticeable to the human brain, the radius of the spinning ring has to be at least 220 meters, which means the diameter of the ship would be over 440 meters. That is a gargantuan structure. And building a colossal ring like that out of strong metals, wrapping it in the radiation shields we talked about last chapter, and packing it with life support systems would require an insane amount of building materials. The mass of a spinning arc like that would be in the millions of tons. And here we come full circle, right back to Chapter 1. The tyranny of the rocket equation will not let us accelerate an object that massive. We are stuck in a catch-22. Without artificial gravity, our bodies will fall apart during the flight, but a ship with proper artificial gravity is too heavy to fly anywhere at all. We are tied to Earth not just by its gravitational pull, but by every single cell in our bodies that requires that pull to survive. But let's say we find a compromise. Let's assume we invent biological drugs to stop bone loss and meds to protect our eyes and blood vessels. Could we go then? Even if we protect the internal world of our bodies, we still have to bring the external world with us. We'll need to breathe, drink, and eat for decades. And that brings us to the next wall of our cosmic prison, the total impossibility of creating a closed, autonomous ecosystem independent of our planet. When we talk about interstellar travel, we usually focus on engines, trajectories, and radiation shields. But we forget about the most basic and simultaneously the most complex aspect of survival. A human needs to breathe oxygen, drink clean water, and eat food. There's no air, no freshwater rivers, no fertile soil in space. A ship heading out into the endless void can't just pack hundreds of years' worth of food and oxygen. That would require thousands of cargo bays, which again hits the wall of not being able to accelerate giant masses. Therefore, the only way out is to build a completely closed ecological system on board the ship. A miniature Earth. An ecosystem where every single carbon atom we exhale is absorbed by plants, turned into oxygen and nutrients, and then comes right back to us. Not a single drop of water or gram of organic matter can go to waste. It sounds like a totally solvable engineering and biology problem. We know how trees grow and how photosynthesis works after all, but reality brutally punishes us for our arrogance. We have absolutely no concept of how complex, multifaceted, and deeply integrated our home planet's biosphere actually is, and how impossible it is to replicate it in a confined space. To prove it, let's look at one of the most ambitious and arguably most disastrous scientific experiments of the 20th century. In early 1991, the construction of a massive complex in the Arizona desert was completed. The project was called Biosphere 2. The name was a not-so-subtle nod to the fact that Biosphere 1 is Earth itself, and scientists were trying to build a fully functional replica. It was a monstrous structure made of glass and steel. Under airtight domes covering about 3 acres, they built miniature versions of various Earth landscapes. It had its own rainforest, a real savanna, a marsh, a desert, and even a small artificial ocean with a real coral reef. It had an agricultural zone to grow food and living quarters. Trapped under the glass were thousands of species of plants, insects, and small animals. The point of the experiment was extremely simple and brutal. 8 people, 4 men and 4 women, had to walk inside this complex, after which heavy airlocks were sealed shut. For 2 full years, they had to survive entirely off what this closed system produced. No fresh air from outside, no food deliveries. It was the perfect simulation of a long-term space flight or an autonomous base on another planet. The project kicked off with huge optimism. The scientists believed their mathematical models were flawless. The plants were supposed to soak up the carbon dioxide the humans exhaled and pump out enough oxygen. But almost immediately, things went catastrophically wrong. Studying this failure gives us a crystal clear understanding of why we will never leave Earth on autonomous ships. The first and most terrifying problem was that the oxygen levels started steadily dropping. Initially, the atmosphere inside the dome, just like on Earth, was about 21% oxygen. But month after month, that number slipped. By the halfway point of the experiment, oxygen levels had crashed to 14.2%. For a human body, that is the equivalent of living on top of a high mountain where the air is incredibly thin. The crew started suffering from constant exhaustion, their sleep cycles broke down, they got horrific headaches, and some could barely climb the stairs. If the level had dropped just a bit more, irreversible brain damage would have set in. But where did the oxygen go? There were more than enough plants, and sunlight poured right through the glass. The scientists on the outside ran themselves ragged trying to solve the mystery. It turned out the creators of the experiment hadn't accounted for microscopic chemical reactions. The soil they had brought in for agriculture was incredibly rich in organic matter. Soil bacteria started multiplying rapidly, feasting on the organics, and in the process, they guzzled massive amounts of oxygen while pumping out carbon dioxide. But the carbon dioxide levels weren't rising as fast as they should have been either. Why? Because another unforeseen factor stepped in. The massive concrete structures that formed the complex's foundation were still curing. The concrete chemically reacted with the carbon dioxide in the air, absorbing it and turning it into calcium carbonate. As a result, carbon was permanently locked out of the biospheric cycle. The plants didn't have enough carbon dioxide to run proper photosynthesis, so they made less oxygen, while the bacteria just kept eating whatever oxygen was left. The balance was completely wrecked by invisible chemical processes. Meanwhile, an ecological apocalypse was unfolding inside the dome. The tropical trees planted in the rainforest grew rapidly upward, but then suddenly fell over, snapping under their own weight. Why? Because there was no wind under the dome. In nature, the constant stress of the wind forces tree trunks to grow what's called reaction wood, which gives them their strength. Without the stress of the wind, the trees grew up brittle and weak. We didn't realize that even atmospheric storms are vital for the structural integrity of wood. Next, the food chain collapsed. Almost all the pollinating insects died off, including bees and bumblebees. Because of that, many of the crops stopped producing food. The crew started starving. On the flip side, there was a population explosion among the pests. The complex was overrun with parasitic ants and cockroaches. They destroyed whatever crops were left and terrorized the crew. The psychological atmosphere inside became unbearable. 8 highly educated, intelligent scientists, locked in a confined space facing starvation and suffocating air, split into 2 warring factions. They practically stopped talking to each other, and things devolved into sabotage and screaming matches. Eventually, Mission Control back on Earth was forced to admit defeat. To save their lives, tons of pure oxygen were secretly pumped into the complex from tanks. The experiment, which cost hundreds of millions of dollars, proved only one thing. We do not have the slightest clue how to run a biosphere. And that was a massive facility on Earth, bathed in natural sunlight, being watched by hundreds of scientists on the outside. Now imagine a generation ship, dark, freezing void, a sealed metal cylinder. If a single strain of soil bacteria mutates on board and starts producing toxic gas or eating too much oxygen, you can't just open a window. You can't ship in new chemicals. If the balance shifts by just a fraction of a percent, the entire colony will die from suffocation or poisoning within a few weeks. Earth's biosphere works because of its colossal scale. We have buffer zones of unbelievable size. The global ocean absorbs excess heat and gases. Billions of acres of Siberian taiga and Amazonian rainforest filter the air. Tectonic plate activity recycles carbon deep into the mantle. This giant machine has incredible momentum and stability, earned through billions of years of trial and error. Trying to recreate this machine on the scale of a spaceship is like trying to recreate the human brain using a dozen transistors. It is mathematically and physically impossible. We don't have the volume, the biodiversity, or the buffer capacity to absorb the inevitable chemical glitches. Because of this, closed deep space ships are doomed to become mass graves. Our biological dependence on a planetary biosystem is absolute. But here, the enthusiasts make their next move. They admit, fine, we can't build a mini Earth inside a metal tube. But why do we need a ship? Let's just fly to the nearest suitable planet, like Mars, and turn the planet itself into a new Earth. Let's start terraforming. This concept has gotten so popular that we treat it like a given. In the next chapter, we're going to break down why the idea of resurrecting dead planets is the greatest myth in modern astrophysics, and why Mars will always remain a toxic, irradiated desert. Alright, so if we can't build a fully functional artificial biosphere inside a spaceship, maybe we should use a ready-made, albeit slightly broken planet. This idea is deeply embedded in pop culture. The concept of terraforming, artificially altering the climate and surface of a celestial body, seems like a logical plan B for humanity. More often than not, Our neighbor Mars is the prime candidate for this epic construction project. We are fed incredibly beautiful and inspiring imagery. The plan usually goes like this. We fly to Mars, build giant factories to pump out greenhouse gases and melt the polar ice caps. The released carbon dioxide and water vapor will create a thick atmosphere. The planet warms up. Then we plant genetically modified lichens and trees that will convert carbon dioxide into oxygen. And boom, after a while, blue rivers flow through the red sand, and the colonists take off their heavy spacesuits and take deep breaths while watching the sunset. This idea was championed by many brilliant minds, including the legendary science communicator Carl Sagan. But as our understanding of planetary physics grew deeper, this beautiful fairy tale started coming apart at the seams, revealing harsh and absolutely unbeatable obstacles. Terraforming Mars isn't a complex engineering challenge, it is a physical impossibility. Let's start with the most important thing. For rivers and trees to exist on a planet, it needs a thick atmosphere. Right now, atmospheric pressure on Mars is less than 1% of Earth's. It's basically a vacuum. If you step onto the surface of Mars without a spacesuit, because the pressure is so laughably low, the water in your lungs and blood will instantly boil, even though it's freezing cold outside. So we need to pump up the atmosphere. But the problem is that Mars didn't lose its air for no reason. It lost it due to a fundamental physical law that we are powerless to fix. Remember Chapter 4, where we talked about Earth's magnetic field and how it protects us from radiation. Earth's magnetic field is generated in the center of the planet, where a massive core of molten metal is constantly spinning. This process creates the magnetosphere, which acts as a force field, deflecting the relentless solar wind, a stream of highly energetic particles blasting from our star. Billions of years ago, Mars had a magnetic field like that too. It was warm, rivers flowed, and seas crashed against the shores. But Mars is much smaller than Earth, and because of its modest size, it cooled down way faster. Its metal core froze and stopped spinning. The dynamo effect shut down. The magnetic shield vanished. The second Mars lost its shield, the solar wind slammed into its atmosphere with all its fury. Solar wind particles smashed into Martian air molecules at massive speeds and literally blasted them out into deep space. This process is called atmospheric sputtering. Over millions of years, the sun completely stripped the planet's air envelope, leaving only pathetic scraps. And this process is still happening right now. Trying to build a new atmosphere on Mars without restoring the magnetic field is absolutely a Sisyphean task. It's like trying to fill a bathtub that doesn't have a bottom. You can burn millions of tons of fuel, melt the ice, and release gases, but the solar wind will just methodically and constantly blow it all right back into the vacuum. Someone might say, let's just build an artificial magnetic field. We'll stick a massive superconducting magnet at the Lagrange point between the Sun and Mars so it casts a shadow over the planet. But we've already covered the energy costs of megastructures like that. Building and maintaining a magnet capable of shielding an entire planet requires technology and resources that exceed the capabilities of our entire civilization thousands of times over. But let's pretend we managed to keep the atmosphere. We hit a second, equally deadly problem: the Martian soil. For a long time, we thought the red dust was just harmless iron oxide, basically rust. But in 2008, the Phoenix lander ran a chemical analysis of the Martian regolith, and the results were shocking. It turned out the surface of Mars is heavily laced with perchlorates. These are salts of perchloric acid. On Earth, these chemicals are used to make rocket fuel and high-grade explosives. For biological organisms, perchlorates are highly toxic. They dissolve easily in water, If Martian dust gets into a human body, the perchlorates will instantly shut down the thyroid gland, cause severe hormonal crashes, and wreck the metabolism. In sci-fi movies, the heroes plant potatoes straight into Martian dirt just by adding a little Earth bacteria. In reality, any plant grown in Martian regolith will instantly soak up these poisonous salts. If you eat that potato, you will be fatally poisoned. To make the soil farmable, we would have to literally wash the poison out of millions of square miles of surface using unimaginable amounts of fresh water, which the planet simply doesn't have. Mars is a global toxic waste dump. The third nail in the terraforming coffin is gravity. As we found out in Chapter 5, our bodies require full Earth gravity. Gravity on Mars is only 38% of Earth's. Even if we magically build an atmosphere, a magnetic field, and scrub the soil, the colonists will still be living in low gravity. Their bones will become brittle, their muscles will atrophy, but most importantly, medicine has absolutely no idea how low gravity affects reproduction. Can a woman carry a healthy baby to term if her internal organs and the fetus aren't feeling the pull of normal gravity? How will the skeleton of a Martian baby develop? There's a massive chance that due to genetic glitches during fetal development, a human population on Mars simply wouldn't be able to reproduce. And anyone who is born and raised there will permanently lose the ability to return to Earth. Their weak Martian hearts wouldn't survive the G-force of returning to normal gravity. And finally, let's look at the timeline. Planetary changes are incredibly slow processes. Even according to the most optimistic theoretical models, if we threw the full might of our civilization at it, building a breathable atmosphere would take about 100,000 years. 100,000 years. The human mind isn't built to operate on those kinds of planning horizons. No government, no corporation, and no economic model can support a project that won't show any results for millennia. Who is going to fund shooting trillions of tons of equipment into orbit around another planet if the rewards won't be reaped until hundreds of centuries later by distant descendants? The illusion of terraforming is incredibly dangerous. It gives the general public a false sense of security. We think that if we push Earth into an ecological collapse, we'll just move to the backup planet. But Mars isn't a backup airstrip. It is a dead, radioactive, frozen, toxic ball of rock that actively fights back against any attempt to bring life to it. We are locked in here. We can't escape on ships and we can't flip neighboring worlds. But what if we try to send not all of humanity, but just a small, hand-picked group of people on an endless journey? In the next chapter, we're going to talk about generation ships and why human psychology and social dynamics make projects like this absolutely unworkable. We'll find out how brutally the genetic bottleneck works and why a closed society floating in the void is inevitably doomed to decay. We have systematically and methodically dismantled the physical and biological barriers. We found out that the speed of light cannot be broken, that radiation shreds cells, and that trying to terraform other planets ends in total failure. And this is where the human mind, refusing to accept defeat, makes one last desperate attempt to find a loophole. Space enthusiasts offer us an epic compromise. They say, fine, we can't fly fast, and we can't alter an alien planet. Then let's just accept the timeline. Let's build a colossal interstellar arc that will fly toward its target for hundreds or even thousands of years. This is the generation ship concept. The people who board the ship when it leaves Earth will never see the final destination. They will age and die in transit. But they will pass the baton to their children, who will pass it to their grandchildren, and so on. Only the great-great-great-grandchildren of the original colonists will one day step out of the airlock onto the surface of a new, untouched world. Sounds incredibly romantic, doesn't it? It's the ultimate sacrifice for the future of humanity. But it's a pretty heavy topic. And the second we start analyzing this idea through the lens of human psychology and sociology, this grand plan turns into the most twisted nightmare imaginable. The thing is, a human isn't just a biological machine that turns oxygen into carbon dioxide. Our minds are incredibly fragile, and they are critically dependent on their environment. Evolution molded our nervous system under conditions of constant sensory variety. We need changing seasons, the breeze, the sound of rain, birds singing, the unpredictability of natural landscapes. Our brains demand a constant stream of new, random information from the outside world just to stay sane and keep cognitive functions running. Now just imagine life inside a generation ship. It's a giant sealed metal tube flying through absolute darkness. Outside the thick glass of the windows, nothing changes for decades. The stars don't zoom past. They look frozen, nailed to the black velvet of the void. Inside the ship, there are endless hallways, artificial lighting, the hum of ventilation, and the exact same faces day after day, year after year. This condition is called total sensory deprivation combined with absolute isolation. And we have hard scientific data on what that leads to. Between 2010 and 2011, the Institute of Biomedical Problems ran a unique experiment called Mars 500. 6 volunteers were locked inside a sealed, ground-based complex designed to mimic a spaceship. The isolation lasted exactly 520 days, the estimated time it would take to fly to Mars and back. The participants were carefully handpicked. They were highly educated professionals with exceptional psychological resilience. They knew that at any moment, they could hit the panic button, open the doors, and walk outside. They knew they were on Earth, perfectly safe. And yet the results of the experiment were terrifying. As time dragged on, the crew started sinking into deep apathy. Their sleep-wake cycles broke down. They talked to each other less and less, preferring to hide in their cramped bunks. Unprovoked fights and bouts of depression flared up. Deprived of outside stimuli, their brains literally started shutting down activity. Their motivation to complete scientific tasks dropped to critical lows. And these were adults who voluntarily agreed to a temporary experiment that lasted a little under a year and a half. Now let's extrapolate that to a generation ship, where isolation lasts hundreds of years, and opening the doors is fundamentally impossible, because there's a lethal vacuum outside. The first generation of colonists, the ones who leave Earth, will be heroes. They have motivation. They consciously chose this path. They remember the blue sky and green grass. But what about their children? The second generation will be born inside a metal box. They never asked for this flight. They were robbed of their home planet before they were even conceived. For them, Earth is just stories from old people and flat images on a screen. But the real catastrophe will strike by the 5th or 10th generation. Let's break this down a bit more. For people who are separated from the launch by 500 years, and who still have another 500 years to fly, the very concept of the destination will lose all meaning. The target planet will become a mythical paradise for them, one that many will simply stop believing even exists. Why bother studying orbital mechanics or astrophysics if your entire world is limited to a mile of metal hallways? Why maintain highly complex nuclear reactors when you no longer understand how they work? In closed, isolated societies, intellectual decay inevitably sets in. Without a flow of fresh ideas, without cultural exchange with the rest of humanity, the ship's society will start dumbing down. Separatist movements, religious cults, or totalitarian dictatorships will pop up. You can't maintain democracy or free will in a place where any mistake, any broken pipe in the life support system means death for everyone. The ship's society will inevitably turn into a brutal caste system governed by draconian laws. And the most tragic part is that the crew might simply forget how to fly the ship. A so-called cargo cult will emerge. People will push buttons and perform maintenance rituals on the engines without understanding the physics behind it at all. If a crucial part breaks, no one from the 10th generation will be able to fix it, because knowledge that isn't backed by real-world Earth practice and university foundations gets wiped out in a couple of centuries. Ultimately, what arrives at the target star system won't be a triumphant expedition of pioneers, but a ghost ship. At best, inside will be a group of feral humans who have forgotten their history and don't even know how to open the landing bays. At worst, the ship will arrive completely empty, because somewhere along the way, one of the middle generations, in a fit of despair, depression, or civil war, simply destroyed the air scrubbers. The psychology of the void is an invisible barrier that breaks the human spirit long before radiation breaks the human body. Our brain is an organ built for Earth, and it won't survive the endless, silent dark of interstellar space. Well, let's assume we found a way to trick the human psyche. Let's say we developed incredible VR systems that will simulate life on Earth for every generation of colonists. Or maybe we use drugs to suppress their emotions, turning the crew into obedient drones. Let's pretend the psychological problem is somehow magically solved. But the second we close our eyes to psychology, we get blindsided by harsh biology. And this time, the problem isn't zero gravity, but the very mechanism of human reproduction. We're talking about genetics. To start a colony on another world or just keep people alive on a generation ship for hundreds of years, we have to send a certain number of people. But exactly how many? 10? 100? 1,000? In population genetics, there's a strict term: minimum viable population. It's the smallest number of individuals needed for a species to survive and reproduce in isolation without degenerating or dying off from genetic mutations. Every single one of us carries a certain number of hidden, recessive mutations in our DNA. In normal life on Earth, this isn't a threat. When two people have a baby, their genomes mix. If one parent has a defective gene, there's a high chance the other parent will provide a healthy copy of that gene, and the child will be born healthy. But when a group of people is isolated in the closed environment of a spaceship, genetic diversity is strictly capped. Biologists call this the bottleneck effect. For the first 2 or 3 generations, things will be fine. But inevitably, a point will come when everyone on the ship is a distant relative. And that's when recessive mutations will start running into each other. Genetic errors that used to hide in Earth's massive gene pool will start popping up in every new generation. The colonists will start having babies with congenital heart defects, hemophilia, compromised immune systems, and severe cognitive impairments. This is known as inbreeding depression. In the middle of space, with no access to Earth's global medical infrastructure, the population will start rapidly weakening and dying out. You can't fix a broken genome with pills or surgery. So how many people do we need to bring to avoid this? In the mid-20th century, anthropologists optimistically guessed that 500 people would be enough to survive. But modern computer models and deep DNA analysis have crushed that optimism. Recent genetics research published in top biology journals shows wildly different numbers. To maintain the genetic health of a population during a 1,000-year flight and the subsequent founding of a colony, you have to send no less than 10,000 people who are absolutely unrelated. And some researchers factoring in inevitable deaths from accidents and disease on board push that number up to 40,000 people. Just think about that number. 40,000 men and women. And here, we run headfirst into a massive conceptual collision with our very first chapter, the tyranny of the rocket equation. Sending 40,000 people isn't like putting them on a big bus. For each of those 40,000 colonists, you need tons of water, tons of food, waste recycling systems, medical bays, surgical tools, living quarters, and the radiation shielding we talked about earlier. You'd have to bring spare parts for every single system for hundreds of years. You'd need education centers and massive tanks of air. Basically, you have to pull a fully functional city the size of a medium Earth metropolis out of Earth's gravity well and accelerate it to colossal speeds. The mass of a structure like that wouldn't be measured in millions, but in billions of tons. To accelerate 1 billion tons to even a tiny fraction of the speed of light would require more energy than our sun puts out in several years. It is an absolute final physics paradox. Genetics demands a huge number of people, and the laws of physics strictly forbid moving masses that gigantic through space. These two sciences crush us from both sides like a vice, leaving absolutely zero chance of escape. But that's not all. Imagine a society of 40,000 people locked in a metal city. To prevent accidental inbreeding, love and the free choice of a partner would have to be outlawed. Reproduction would turn into a cold, strict mathematical process. The ship's computer would analyze every resident's DNA and issue directives. Passenger 3,200 is required to conceive a child, with passenger 8,400 to maximize genetic distance. And absolutely no exceptions. That would mean the complete abolition of basic human rights. The abolition of free will. The abolition of the family structure as we know it. A human being would become a simple incubator for passing on genes, totally subordinate to survival algorithms. Could a society like that, built on total eugenics and coercion, hold on to what we call humanity? That's a huge question. The genetic bottleneck proves that our biology is designed to exist only on the scale of a massive planet with a population of billions. We can't chop our species up into little pieces and ship them off into the void. A cosmic arc is a utopia that shatters the moment it bumps into the laws of inheritance. We've covered physics, biology, and psychology. We've seen how the fundamental laws of nature build impassable walls around Earth. But even if we lived in a perfect universe where rockets flew on water, radiation didn't exist, and people could photosynthesize sunlight, one last, deeply cynical and bulletproof barrier would still stand in our way. We are talking about economics. We rarely think about it when we read sci-fi or watch rocket launches, but in the real world, absolutely every human endeavor is subject to the harsh rules of resource allocation. Not a single ship will lift off from Earth unless someone pays for it. The media often makes bold claims. Space is the new gold rush. We're told the first trillionaire in history will make their fortune mining asteroids. They tell us about giant chunks of rock flying between Mars and Jupiter made entirely of platinum, gold, and rare earth metals. It feels like all we have to do is reach out, and it will rain limitless wealth on humanity, easily paying for any interstellar travel. But let's look at this optimism through the lens of basic macroeconomics. It's a pretty heavy topic, but it clears things up really fast. There is a fundamental economic rule called the law of diminishing returns. Let's say you discover an asteroid in space that contains 1 million tons of pure platinum. On Earth, platinum is incredibly expensive. You raise massive capital, build an ultra-complex mining ship with radiation shielding, burn ridiculous amounts of money on fuel, and send the mission out into deep space. 10 years later, your ship successfully mines the asteroid, fills its cargo bays, and returns to Earth orbit. You drop this 1 million tons of platinum down to the surface. You expect to make insane profits and become the ruler of the world. But what actually happens? The exact second 1 million tons of new platinum hits the global market, supply massively outpaces demand. Platinum is no longer a rare, precious metal. Its price crashes at cosmic speeds. It becomes cheaper than aluminum or iron. You spent trillions of dollars funding an incredibly complex interplanetary mission, and you brought back a material that is now worth pennies. Your corporation instantly files for bankruptcy. This paradox destroys any economic motivation for deep space exploration. The cost of fighting gravity and distance will always be astronomically higher than the value of whatever resource you can drag back. There is nothing in space that we couldn't mine or synthesize right here on Earth for way cheaper. Yes, the planet's resources are finite, but recycling a landfill in the middle of Europe or extracting metals from seawater will always be thousands of times cheaper than flying to the asteroid belt for them. Now let's apply economic laws to the project of building an interstellar colony ship. We already figured out that to save a population, we need a city of 40,000 people, weighing millions of tons, equipped with radiation shielding and artificial biospheres. Building a behemoth like that would require the combined effort of the entire Earth's economy. We'd have to divert a huge chunk of the global GDP into mining metals, creating new fuel, and building orbital shipyards. That would mean a drop in the standard of living for all 8 billion people on Earth. People would be forced to eat less, consume less, and give up comfort for one single goal: building a giant tube that's going to leave forever. But who is going to invest in this project? The human economy runs on the principle of return on investment. Governments plan budgets a few years ahead, driven by election cycles of 4 or 6 years. Private corporations and investors want to see profits in 5, 10, maybe 20 years tops. An interstellar flight will take millennia. The ship we build by bankrupting our home planet will never send back a single gram of resources or a single scientific discovery within a reasonable time frame. For the Earth's economy, launching a ship like that is the exact same thing as gathering trillions of dollars, piling them into a giant mountain, and just setting them on fire. It is a pure, unrecoverable loss. No economic model, whether it's capitalism or a planned economy, can support a project that works exclusively for the distant future of abstract descendants, while starving the generation alive right now. We only build things when they pay off here and now. Communication satellites make money for telecom companies. Weather satellites save agriculture on Earth. Orbital telescopes give us foundational knowledge, boosting national prestige. All of this happens close by, right in our own orbital backyard. But deep space is absolutely unprofitable. It is a bottomless black hole for capital, labor, and intellect. And as long as humanity is constrained by the concepts of resources and energy, we will never be able to justify building an interstellar ark to ourselves. So the walls of our prison aren't just made of physics equations and DNA double helixes. They are also built out of the unbreakable laws of economics. We are locked in here by the math of resource allocation. But does that mean nothing at all will ever leave the solar system? Does that mean Earth will permanently remain a totally isolated island? Maybe there is a way out. But taking that way out will require us to give up the most precious thing we have, our very own biological nature. In the next chapter, we're going to talk about post-biological expansion and the concept of von Neumann probes. We'll find out why, if anyone is going to inherit the galaxy, it definitely won't be us. There is one pretty radical concept that lets us bypass absolutely every physical and biological barrier we've talked about so far. But the price of this solution is totally abandoning our humanity. We are talking about what's called post-biological expansion. To get the core of this idea, we have to look at the work of the brilliant 20th century mathematician, John von Neumann. This outstanding scientist made massive contributions to quantum mechanics, economics, and the creation of the first computers. But what we care about is his theory of self-replicating automata. Von Neumann proved mathematically that it's possible to build a machine that holds its own blueprints and has the ability to pull resources from its environment to build exact copies of itself. Let's imagine a space probe built on this principle. This isn't some giant generation ship with a biosphere, water, and thousands of people on board. It's a relatively small, compact, and incredibly tough piece of hardware. Inside, there's no air, no food rations, and no life support systems. It doesn't need to spin to fake gravity, because its circuit boards and titanium parts don't suffer from bone decay. Most importantly, this probe doesn't care about cosmic radiation. Where a heavy galactic ray ion would shred a DNA helix and trigger terminal cancer, the most it can do to the probe is fry a microchip, which the probe will instantly reroute to a backup circuit. It doesn't need lead shields several meters thick or giant tanks of water. This makes the probe lightweight. And since it's light, we beat the tyranny of the rocket equation. We can use powerful ion or nuclear drives to accelerate this machine to serious speeds without burning through an entire planet's resources. But the most mind-blowing part happens when this von Neumann probe reaches another star system. It doesn't need to hunt for a planet with the perfect atmosphere, a magnetic field, and the right gravity. Any dead, lifeless asteroid or rocky moon will do just fine. The probe lands on the surface, fires up its drills, and starts mining metals and silicon. Powered by the local sun or an onboard nuclear reactor, it processes the raw materials and 3D prints parts out of them. Step by step, piece by piece, it builds an exact copy of itself. Then another one. And another. Every single one of these new copies, loaded with the same software, blasts off toward the next star systems. The cycle repeats. One machine makes two make four make 8. It's classic geometric progression. According to mathematical models, even if these probes travel at just 10% of the speed of light and spend a few centuries mining in each new system, they could colonize the entire Milky Way galaxy in just a few million years. A few million years is an eternity for a human lifespan, but it's just a brief blink on the cosmic timeline. And this brings up a deep philosophical paradox. If we humans ever manage to reach the stars, it won't be in spacesuits standing on the decks of shiny starships. It will happen as lines of code uploaded into the silicon brains of immortal machines. Maybe our biological species is just a middleman, a stepping stone in evolution. We are the biological bootloader. Our only cosmic purpose might be to evolve just enough to invent artificial intelligence and self-replicating machines, and then quietly live out our days on our home planet, leaving the real expansion to those who are actually built for it. Machines don't get bored. They won't go insane from 1,000 years of isolation in the dark void, like we talked about in Chapter 8. They aren't threatened by inbreeding depression or genetic decay from Chapter 9. They couldn't care less how much platinum costs on Earth's markets because they aren't part of our economy, which we broke down in Chapter 10. They live by a completely different set of rules. They are the ultimate colonizers. They can sleep for 1,000 years during the flight between galaxies, cutting all power except for the wake-up timers. And when they arrive, they'll wake up, analyze the spectrum of the nearest star, and get to work. Post-biological expansion solves every physical and logistical nightmare of interstellar travel, but it entirely cuts flesh and blood humans out of the equation. We will never set foot on the sands of exoplanets. We will never breathe alien air. If anyone is going to watch the sunsets of alien stars, it will be camera lenses beaming data back to freezing cold server farms. Space romantics usually hate this conclusion. We want to be the heroes of this story ourselves. But the harsh truth is that the universe is not tailored for carbon-based life forms that are tied to a narrow window of temperatures, pressures, and gravity. The universe is a realm of radiation, vacuum, and extreme energy. And the only entities that can survive in that realm are the ones built from the ground up out of steel, titanium, and data. The concept of von Neumann probes is elegant and logical, but it inevitably drags us toward the biggest, most terrifying question in modern science. A question that ties all our previous chapters together and forces us to look at our place in the cosmos with genuine dread. If self-replicating machines can colonize the galaxy so easily, and if physical barriers only stop biological life, then where is everybody else? In the next and final chapter, we're going to crash into the Fermi paradox and the concept of the Great Filter. We'll try to understand why the deafening silence of the universe is the strongest proof that we are locked on Earth forever. We've come a long way. Step by step, we've analyzed the walls of our cosmic prison. We saw how the tyranny of the rocket equation stops us from lifting heavy payloads into space. We grasped the true paralyzing scale of the void, which makes any journey agonizingly slow. We hit Einstein's energy barrier, which refuses to let us fly faster. We learned that invisible radiation shreds our DNA and zero gravity dissolves our bones. We realized that building an artificial biosphere is impossible. Terraforming is a pipe dream, and psychology and genetics forbid us from sending generation ships. And even when we found a hypothetical way out in the form of immortal, self-replicating machines, that solution cut us right out of the equation. All of this brings us to the final chord, to the answer of the greatest mystery in modern astrophysics, known as the Fermi paradox. In the mid-20th century, the brilliant physicist Enrico Fermi was chatting with colleagues about the chances of alien civilizations existing. And he asked one very simple but absolutely devastating question. Where is everybody? If even one of these ancient civilizations had decided to start expanding, whether biologically or post-biologically using von Neumann probes, they would have colonized every cubic parsec of the galaxy a long time ago. We should be seeing their giant megastructures picking up their massive radio broadcasts and bumping into their automated bases on every asteroid in our solar system. The galaxy should be buzzing with activity like a giant anthill. People sometimes assume that the Great Filter is a nuclear war, an ecological catastrophe, or an AI uprising. It's believed that advanced civilizations simply killed themselves off before they ever managed to venture out into space. But what if we're wrong? What if the Great Filter isn't one single catastrophic event, but rather the exact combination of physical, biological, and economic laws we've been analyzing in detail throughout this entire video? Realizing the fact that we will never leave Earth shouldn't cause despair. On the contrary, it should become the greatest call to action. If this is our only home in the cold, deadly void, and if we know that we don't have and will never have a backup planet, maybe it's time to stop dreaming about conquering dead Martian deserts and start taking care of the one oasis of life we were lucky enough to inherit. I wonder if humanity ever truly realizes that this planet is our final and non-negotiable destiny. Will it force us to change our attitude toward it? The answer to that question remains open.